So this is a first come, first serve. Nothing that complicated, nothing difficult. Okay, as you imagine for the first, but I'd like to introduce how it works for future the scheduling algorithm later. So this is one of the best way to understand. Then the reason why I'm doing this is eventually you should be able to implement this kind of the algorithm in your programming code. How can you do that? You can define class for the PCB or data structure, or in case of C or C++, struct. Okay, you can define the PCB. Then you manage to create the queue. Then the state at the PCB you can specify such a state. Then the main scheduling algorithm running while using the while loop. Then the check if there is no the process in the running state, then the select using the arrival time select. Okay, so this is how it works. You are able to implement it. It's really implemented in the all the operating system. Okay, then one more thing is we are going to evaluate how much fast is this using waiting time and response time. So for the waiting time, we need to calculate the waiting time of the P1. So what is the total waiting time of the process 1? It alive time 0 and pick up time 0. No waiting time. What about P2?
24.
It's the arrival time is the 1. It's the pick up 24. So 24 minus 1. So 23. What about P3? It's the selected 27 arrival time. It's a 2. So 25. So total waiting time is 0 plus 23 plus 25. Divide by 3. Average waiting time is 48.16 millisecond, whatever. And response time. Response time is the first response, first selected. So P1, 0. P2, 24 minus 1 is a 23. P3, 25. Then the response time, average is 16. Okay.
So that's the same calculation for waiting time.
Yes. Why is the same?
Because it's non-preemptive.
This is a non-preemptive, means once started, no waiting time in the middle. The only waiting time is the first selection until the first selection. So for any non-preemptive case, the waiting time is the same as the response time. Okay, that is one tip to understand this. But preemptive may be different. We will see later. So it takes the 16 average waiting time. It takes the 16 response time. If I ask you to improve the first come first serve, so first come first serve, what is the benefit, do you think, advantage of using the first come first serve? Is the any first come first serve?
Yeah.
It's kindly fair, right? It's kindly fair, and also always easy to. Because of that first come first serve, really used a lot in any computer system as an algorithm. Not only for scheduling, any such the kind of computation. It's fair because it's a arrival time we consider. It's simple to implement. So that is a benefit. Problem?
Average waiting time is more process starvation.
As you can see, the process 2. Let's suppose that the P1 is the student 1, P2 is the student 2, and so on. And it's the advising. So P2, P3 need signature. But because of 1 second, the first student need a lot of time for discussion on the thesis. So 2 hours. So it's not fair. So because of 1 second, I need to wait 2 hours. Okay? Because of that, these two processes wait a lot of time. Because of that, overall, the average waiting time, overall average response time is very high. Okay? So this is the problem of first come first, especially the non-preemptive case. So this is called the convoy effect, which means the amount of the CPU burst time process will be hidden by the long running process. Okay? That's the same problem in many. So if you go to the Walmart, so sometimes you are purchasing only the couple of items, but there's long line. And not long queue, so 1 or 2. So you go to that register, but it takes long time. It's full of the cart. Okay? At that time, some of the customer, ask the pass through to the checkout, the couple of items, more item, less item. So this is called the convoy effect. Because of that convoy effect, it takes a longer time. Okay. So to address that one, if we change it, for example, in case we change the order, like the P2 alive first, P3 alive, then followed by the P1, it's exactly same. The CPU burst time, the CPU time need, but the different order. I'm not going to calculate again, but if you follow the same direction, the average time is the 2, waiting time is the 2. Even though we do not change the CPU, it's the same CPU time, different order, it will be huge different. So this is called the convoy effect. So long running process will hide the short running process. Okay, so that is the first come first serve, and it's not very good for the time, the sharing operating system because of the convoy effect. So next one is, what is the idea of to address such a convoy effect problem? Instead of arrival time, we will take a look at the CPU burst time. Okay, so that is called the shortest job first. We are going to take care the student who need just a signature, okay, from the queue. So let's use this example to do the ready queue, running queue, and this. So we did the first come first serve, the shortest job first. So in the shortest job first, there are two options. One is non-preemptive, another one is a preemptive case. So we are going to start from the non-preemptive case. So this is a process state. You can see the process ID, arrival time, and the CPU burst time. So let's start from the process 1. So process 1, alive, P1, alive, the time 0, CPU burst time 7. So current time is the 0. This is the current state. So CPU scheduler, choose the first, we select this one. So P1 move to the running. This. Okay, then no one, P1. Then next P2 is alive, time 2. So time 2, this is time 2, P2 alive. So P2 is the, what is that? 2, 4. First, we are going to use the non-preemptive case, which means once process 1 is started, it will be terminated. So even though P2 is alive, CPU scheduler cannot do the context switch. So this is the time 2. And the P1 is still running. And at time 4 and 1. So time 4, the P3 is alive. Still, it's not changing because it needs the 7. And the time 5, P4 is alive. So currently time 5, still P1 is running because it's a non-preemptive case. We will see preemptive case later. So currently it's a time 5 until when? Time 7. At time 7, finally the P1 is terminated. Then, so P1 is up to here. At time 7, the CPU scheduler select the next process using what? Arrival time? No, this time amount of CPU, the needed CPU burst time. So P3 will be selected. So P3 will move to the running. So P3 will be here. How long?
1 second.
So 1 second, so time 8. So time 8, it will be terminated. If needed, you can add the terminate time. Okay, here. So in your PCB always. Or we can manage over here. So next, at time 8, P2 and P4, both of them are the same. So you can always have the type right rule. So usually type right rule is simplest one. In our case, we are going to use the first come first serve. Okay, the arrival time. So P2 is selected. So P2 is selected. P2 until when? 4 will be 12. So P2 will be done. So whatever. And the 12. Then finally P4 is selected. And P4 until P4 is what? 4. So it will be 16. Okay. So then it's that all of them are terminated. Let's check the average waiting time and the response time. Do I need to calculate both of them? This is non-preemptive case, so we can do either of them. So let's check the waiting time. So waiting time P1, 0. This is selected right away. P2 is P2 alive 2 and P2 started 8. So 8 minus 2, 6. P3 is selected 7 alive 2. 7, 4. It's a selected time. So alive when? P3 alive the 4. Yes, 7 minus 4. Then this is the 3. And P4 alive the 5. Selected the 12 minus 5. It's going to be 7. So add 0 plus 6 plus 3 plus 7 divided by 4 is 4. Average waiting time 4 and response time is also automatically 4. This is the shortest job first non-preemptive case. Okay. Any question? Then next we will go for the preemptive case. Means whenever there exists the event, we will check what? Remaining time. Remaining CPU time. Okay? Because preemptive case, the process can be stop, pause, then the resume later. It can be back up. So we can consider such a remaining job first. So that is called the preemptive case, the shortest job, or this is sometimes called the shortest remaining job first. Okay, so shortest remaining job first. Preemptive, shortest job first. So remaining job first. So we are going to use the same process state. Then we will check the shortest remaining job. So P1 is alive 0 with 7. So then it will be selected time 0 and right away it will be selected time 0. Then it will be running until when? when the process 2 is alive. The process 2 is alive, the 2 and 4. Okay? The time 2. At that time, P1 will be back to the ready queue. It's a preemptive. It's a backup. Then CPU scheduler will select the next one. Then arrival time is 0. Instead of the CPU time, total time, remaining. What is the remaining time? 7 minus is running until the 2 is 5. So 5 will be. So this is the current status of your computer at time 2. Then the shortest job, remaining job will be selected. Which one will be selected? P2 is less than the P1, so P2 will be selected. So P2 is removed from here. Then P2 is selected. Okay, until when? 3 is okay. 4. At time 4, what happened? P3 is alive. So P3 alive, time 4 with the CPU burst time is 1. And then P2 is back to here. What is the remaining time? 4 minus 2 is run the 2 time slot like this. So this is the current state of your computer. At time 4, we are going to select next process using what? Shortest remaining. Which one? P3. P3 will be selected like this. And until when? P5, at the time 5, this one is terminated. So P3 is terminated. Okay. Then P4 is alive with the CPU burst time is 4. Then CPU scheduler select the next one based on what? Remaining time. So which one will be selected? P2. So P2 is selected. Is there any other event later? No. So there's no more. But in real case, real life system, a lot of in and out. So scheduler should run the certain period of time. But in this case, it's an event. Only based on the event. So current time 5. So this is a P3. And then the P2 is selected. So this is a P2 until when? 2 time slot. So 7. Okay. So P2 is terminated. Then next, from the ready queue, P4 is selected. P4. And how much? 4 times slot. 11. So 11, this one will be terminated, P4. The last one is a P1. So P1 will be selected, and the remaining time, 5, so 16. So 16, finally, it's a move to the running, and the P1 will be terminated. Okay, then, check the performance using the average waiting time and average response time. So this time, average waiting time is different from the response time. First, check the response time. What is the response time of the P1? P1 alive the time 0 and selected the first response time 0, which means it's a 0 response time. What about P2? P2 alive the time 2 is selected time 2. So 2 minus 2, 0. Process 3, alive time 4 and selected time 4. Response time is 0. P4, alive the time 5 and selected 7. It's 7 minus 5, 2. So total average 0, 0, 0, 2 divided 0.5. Okay? Very quick response time. And what about the wait time? process 1 is selected 0, no waiting time, but until terminated this amount of time, from 2 to 11, P1, 11 minus 2 is the waiting time. Okay? So waiting time and response time is different in this case. P2 is selected right away, no waiting time, but between 4 and 5 is the waiting time of the P2. So 5 minus 4 is 1. P3 is selected right away and terminated, no waiting time. P4 is alive 5 and 7. So 7 minus 5, 2. So total 9 plus 1 plus 0 plus 2 is divided by 4, 11 over 4. 9, 1, 2. 9, 1, 2, not 12. So 3. So waiting time, average waiting time of the shortest, the remaining job, or shortest job first with the preemptive. Preemptive should, it's the same thing. Okay, don't be confused. So some of the students, if I ask the shortest remaining job first, so this is the same as preemptive, shortest job first. Okay, so this is the another algorithm. Advantage. What is the pros of this algorithm? Very quick response time, because it's anyway will be selected if that has the last remainder CPU time. Okay? And problem. Actually, this is not the only problem of this one. The first come first served, and the shortest job first has the same problem.
If it is longer, then it has to wait till every short process.
You have to.
Not good means, which is not good? Process is not good.
No,
Well,
Dr.
it-
Albert, like if the process has a longer CPU time
Huh?
and always some shorter CPU time process
Okay,
is
oh,
then it is always.
Yes. So for example, if like in this case the P1, it will be the move back if there is any, the process is a short amount of time. It may be the starvation problem. Okay, that's also good, the comment. Any other issue? There is a really big issue
You
in
have
this
to
example.
store every time the process state. Like when you are cutting the process, pausing the
That
process.
means we have the context switch.
Yeah.
That's the overhead. But in our example, we do not consider the overhead, but real application, yes. So that's another issue. The biggest issue of the algorithm is, how do you know the CPU burst time? Is it possible? When you can estimate what roughly. So today it may take a longer time, okay, to see the Professor Lee, okay, because I need to discuss about the thesis and all my future. But if I get the signature only, it may take the shorter time. You can guess. However, you cannot know the future, how long it takes. Think about the application program. Sometimes it starts quickly, but sometimes it takes a longer time to start your computer, you start the program. So actually, practically, it's not possible to know burst time. The previous one is the same thing. Arrival time, we don't care. The CPU burst time is not important. But in this case, the remaining time, how do we know the remaining time? It may be longer, it may be shorter. Okay, so that is a problem. However, nowadays we are living kind of the prediction of uncertainty, the nature, right? You can predict even stock price, right? You don't have to be here, so you can trade. So also, if you are taking the machine learning, data mining course, or if you are interested in the data science, always our goal nowadays is, can we predict something? Okay? Can we see the future. That is our ultimate goal of such a data science, data analytics, or the data mining, machine learning, AI, deep learning, like that. So, however, even before the machine learning era, the statistician actually predict the number or the pattern of the data using kind of, for example, regression. Using if data is like a 1, 2, 3, maybe it's a 4 later. It's we can predict. So there is the algorithm to determine the future based on the previous history. So it's not very complicated. We are going to adjust from the previous data. Using the previous data, adjust. So this line is the prediction. The black line is the prediction, and this is real CPU burst time. We can reasonably predict. Okay. Nowadays, more complicated algorithms are used. That's very important nowadays. So when we are using the cloud, the system, if you offer the cloud service, you don't want to purchase all the CPU, all the memory that are needed for all the customer. Instead, you try to maximize, but you need to predict how much do you need CPU, how much you need the memory, and so on. So such using the prediction, you can allocate the physical hardware to minimize the waste of time, okay, waste of resource. So that is the idea of how to predict. Okay, I'm not going to cover the details of it. This is based on the adjust. So very similar as yesterday I told the neural network. So backpropagation actually adjust. It's the kind of adjusting based on the previous data. For that. Okay, the next one is the priority. So priority is not actually the new one. Think about the first come first serve. What is a priority? Arrival time. Shortest job first. What is a priority? CPU burst time. And the shortest remaining job first. What is a priority? Remaining CPU time. So any such a selection algorithm, actually we can regard such all the algorithm as the priority based. The problem is what is a priority? But if we specify the explicitly priority number, like this student is very important, priority 0. And this student I can ignore because he didn't pay attention, so priority 100. So regardless of such a characteristic like the arrival time, whatever, just explicitly assign the priority number. Then we are going to use the priority number for the selection. So first we are going to, I'm not going to use this one to speed up, because it takes a long time, but you are able to understand and use. Please use the handwriting for 1 or 2 times at least to prepare your midterm exam. Then you can understand the algorithm. So this is our process state. We, in addition to the arrival time and CPU burst time, assign the priority. Higher number, higher priority. Usually lower number is the higher priority. Reason is that if we use the opposite way, higher number, you can add up. It will be highest, there is no highest. So we have the maximum highest priority, which is the 0 usually. Okay? Then lower priority is the higher number. So in this case, which one is the highest? This one is the highest priority. But so we can consider both the non-preemptive and preemptive also. Non-preemptive, once you start, like the P1 is, even though the lower priority, it will be the running until terminate. Okay? Then this time 19, we have 2 processes in the ready queue because they allow the 2 and 4. Then at the time we can select the next process using the priority. Which one will be selected? P3 because it has a higher priority. Lower number of priority. Don't be confused. Some of the students confused this one. Most of the all computer science, the algorithm use lower number as the highest priority. So P3 then followed by P2. You can calculate the waiting time, and in this case non-preemptive, so their waiting time is the same as the response time. It's 13. Average is 13. What about the preemptive? So P1 will be selected anyway at time 0 because it's the only process. But when P2 is arrived at time 2, you need to check from the reticule priority. So P2 is the higher priority. P2 will be selected. Until when? At time 4, the P3 is arrived, so you need to check the priority. So this one will be selected, and so on. Then if you calculate the waiting time, and so you can calculate. Then, what will be the problem of this algorithm? It's not actually only the scheduling algorithm, problem of the scheduling algorithm, but also it's generally any algorithm that are using priority. It's the starvation. So starvation is always the problem, which means it cannot be selected. Like the previous example, so if short learning job will not be selected in the first, the shortest job first. No, long learning job. Higher the CPU version will not be selected. That is a starvation. Okay, always any priority-based algorithm has a starvation. In general, to address the starvation problem, aging. Aging means at certain time, if not selected, promote. Next priority. If not selected, next until when? Highest. Eventually, it will be processed. So that is called the aging. So we can use the aging. What about the windows? If you go to the task manager, okay, each process has if you right click, what you can see? Highest, real time, higher, normal. Can you see that? That is actually priority. So Windows use the priority-based scheduling algorithm. The problem is, who decides the priority? That's the problem. So user can specify, as a default is normal, but you can explicitly change the priority. But there is always a warning sign. It may cause a problem, but it may not cause the problem. You can change it. But the real time is it will be selected always. The problem is it's kind of starvation of other process. Okay? And also, operating system, if you later we will see some of the process are the system process should run. So at the time, the operating system firstly assigned higher priority will be running. Yes?
What happens when we have the same priority? For example, if there are two processes that's in the ready queue,
Then
priority 2.
That's not the only, as I said, this kind of algorithm is not only one. Okay, we combine several algorithms together. Like for the tiebreaker, we can use the shortest job first. Or sometimes first the shortest job, then the priority, and so on. So you always combine hybrid approach. Also, we will see some multi